Hello, everybody. My name is Nikos Dimitrakopoulos. I work as a senior solution engineer for Altair Engineering from our offices in Athens, Greece. And in today's webinar, we're going to discuss efficiency maps. The title of this webinar is Fast Track eDrive Efficiency Maps with PSIM and HyperStudy. No DU setups, no scripting. So, without any further ado, we can start with the agenda. And while we are waiting for more attendees to log in, we can also maybe create some polls. And I would be really curious to see your answers and see what you guys are working on. So in this session, we're going to discuss what are efficiency maps, why efficiency maps are important for any eDrive. We are going to get into the different ways you can create efficiency maps with PSIM. And we are going to discuss a new approach which involves creating an efficiency map without any scripting with Altair's tool called HyperStudy. The first example we're going to investigate will be with a linear machine, but then we're going to increase the fidelity and use a non-linear machine, also including effects from an FEA tool from the Altair umbrella called Flux. And we can discuss how we can maximize the fidelity to simulation time ratio for this, let's say, a bit more complicated simulation of drives. Then we're going to discuss how we can work with multi-dimensional efficiency maps, and we're going to actually create a fit model, a reduced order model of such a map, and deploy it in a system-level simulation to run a WLTP cycle that will help us, for example, investigate the range of a vehicle. This webinar will be recorded and it will be uploaded to YouTube along with the examples and simulation files we will discuss today. The slides should be already be provided to you with the webinar link, but they will also be uploaded in the same space along with the simulation after the simulation files after the webinar is finished. So I will start with some polls to since this go-to interface is not very interactive in terms that you cannot really open your microphones and ask questions or present yourselves. I will launch first of all a basic poll or what is your industry, the industry you are working on. Please feel free to complete the answers in order to maybe also adjust a bit the content and the exact topics we will discuss today. I also see that more people are coming in, so this is nice. I'll wait for a few more seconds until a good percentage of the attendees have responded to the poll. I see a lot of automotive people. I'm not sure if you can see the answers, but right now 40% of the attendees is with automotive. We have some heavy equipment and off-highway attendees, industrial drives, and aerospace as well. Okay, so let's move to the next one. So another good question is what are the current tools you are using for power electronics right now? So the options are PSIM, Simulink, Plex, ANSYS, or SPICE. I'm surprised to see that over 30% of our attendees are working with SPICE. This is interesting. 60% is PSIM, Simulink is 40%. I'm really excited for the SPICE attendees to see what we have prepared today. By the way, let me also say that PSIM can co-simulate with Simulink in case you want to have your control stage inside Simulink and work with PSIM when it comes to the power states. The heavy loading of the simulation for the switching part will be handled by PSIM, and Simulink will only have to handle the control and the sampling rate. Okay, I'm going to end and share the results. And final poll for today, I see more people coming in, is how do you currently create efficiency maps? I'm also really curious to see um, the different ways you are currently implementing. From experience, I see a lot of people working with scripts, MATLAB scripts, Python scripts. I see a lot of people working with Excel and lookup tables, uh, even experimental data. The options are Python, MATLAB, Excel/lookup tables, Altair tools, and manual/experimental data. I see that the majority of our attendees are working with Altair tools, so um, maybe most of our attendees is our working with our is part of our user base. But I also see some people working with MATLAB scripts and Python scripts. Okay, so I believe we should be okay. I'm going to close the polls and move on with the webinar. So, some news in case you haven't heard. Uh, Altair was recently acquired by Siemens. The deal closed in March 2025. And to provide you with a bit of history, the original founder of PSIM, uh, Dr. Hua Jin, started PSIM, founded PSIM like in the early 2000s. Dr. Jin is still with us, working with us as part of the development team of PSIM. PSIM was then acquired, and PowerSIM as the company were acquired by Altair in 2022, and now Altair has been acquired by Siemens, um, which hopefully will bring a new range of capabilities, including tools in the PCB side of things, for example, since PSIM is just covering the schematic 1D side of simulation of power electronics right now. Okay, so first part, introduction to efficiency maps. What is an efficiency map? So here I have a car. I know our attendees are not only with the automotive sector, but you can imagine a general drive that is constituted of a DC stage, an inverter, and a motor, and then we have the control. And all of these drives, when it comes to the machine, it will have a torque speed envelope, which basically defines what is the torque it can hit for every speed point. This envelope is divided in two parts. First is the constant torque part, and then is what we call the constant power part. Maybe it's not exactly constant power, but this is how we call it. And this point here is called the knee point, where we have to start applying some field weakening if we want to hit further speeds from down here because of back EMF constraints. So when it comes to an efficiency maps, what we basically want to do is automate simulations or even do a lot of experiments if we're talking about hardware, where we have the drive reach the steady state for different combinations of speed and torque. Basically, we want to uh, uh, uniformly distribute points inside this torque speed envelope and calculate the efficiency at steady state for each point. Now, for that, we need, of course, steady state to be hit successfully. We need to be able to hit every point within this envelope, and this is not always easy. We're going to discuss some tips today. You need, if we're talking about simulation, you need a robust and fast tool in order to do this, because we're talking about automating a lot of simulations, and you want them to be fast and you want them to converge. This is where our SPICE users may find the PSIM workflow much more user-friendly, for example. And then you also need to calculate the inverter, motor losses, and also other losses including the system to come up with the system level efficiency. But what if you want to test different things inside your drive, like test different semiconductors, IGBTs versus MOSFETs, different motor designs even, for example, use more turns for the stator winding. What about the switching frequency or even the modulation technique? So in that case, what I see in many clients who haven't been introduced to Altair tools is they just create scripts and they automate the process all over again with the simulation having a different switch or having maybe a different PWM technique. When it comes to the motor, if you want to include high fidelity effects, things are not that easy with other vendors compared to Altair because Altair has the unique characteristic that it includes an FEA motor design tool in the same umbrella, which is called Flux. And we will discuss about Flux later. Now, the solution we provide is instead of having a 2D like efficiency map, you can have a multidimensional one. As you can see, this is this captures the inverter losses, but capturing the efficiency would be mostly the same. The speed and torque is in the X and Y axis. The inverter loss is in the Z axis. And you see that the points are distributed in three different categories because we have different semiconductors. For example, there's a drop-down list where you can change the semiconductor and see exactly how the losses change. You can change the case temperature, which directly couples with the cooling of the inverter. And you can also change the gate resistance multiplier. The gate resistance is a trade-off between losses, switching losses to be more specific, and EMI. Um, so why are efficiency maps important? Uh, let's talk first automotive. Let's say you want to buy an EV, an electric vehicle. Oh, I see that there is no audio. Can you all hear me? Okay, there was a question that, uh, okay, thank you for letting me know. So yeah, automotive. Let's say you want to buy an electric vehicle. Uh, what is the first, or let's say, what are the first things you look into? Of course, is the price, and we can also include the price. I can show you that later inside our studies here, but also the range. You want the car to be able to go in a big distance without having to charge it here and there. The range couples directly with efficiency, and efficiency is a big part of, it's a big key performance indicator when it comes to the drive design. When it comes to industrial drives as well, this is important because less efficiency translates to more operational costs for a drive working in a factory or something. Um, and the nice thing about eDrives is that there are a lot of trade-offs to be made. Uh, for example, you cannot really know from the beginning when you size a car how many motors you want. Uh, if you can use like a different battery or even a different gear ratio in order to maximize the efficiency, but at the same time hit all the requirements you have for the vehicle. Basically, in order to be able to go up to your upper management and show the optimal options, you need to explore the design space. And efficiency plays a key role in that and in the system trade-offs in general. Uh, I have two use cases. For example, you want to size a drive and you have different battery pack options with different configuration of series or parallel or even different batteries. And you also have different gear ratio options. And you also want to design a machine and you don't really know how to optimize the envelope of the machine when it comes to the constant torque and constant power region, how many turns to use and all that. So questions you may have are, what if you could eliminate, for example, the rear drive with a specific front gear ratio selection? What if the battery selection prioritizes mass reduction to use less battery in order to pass a gradient test? If you want, if you have a specification to start in the hill, and what if you can adjust system level choices in order to enable more favorable choices for either the inverter selection or the motor design. So if these questions resonate to you, you're in the right place. And I wanted to discuss a realistic example we did. This is in our community, and I will also show it later. And I can also share the simulation files for this regarding the new innovative Kia EV9 drive. So there was a lot of speculation around this drive because there were some pictures with the motor having all 6 winding ends exposed. A lot of people were saying that this is like a delta versus star transition. But in fact, what Kia seems to be doing is they used 2 inverters per 1 motor. And the reason they did that is because when you use a second inverter and you connect it to the end of so you use an open winding configuration for the PMSM, it's like effectively increasing the available voltage, which means that you can optimize, or you can have more favorable uh, design trade-offs for the motor. For example, you can increase the turns of the machine, of the stator windings, and not suffer from the same back EMF constraints in highway mode, let's say, because you can add the second inverter, double the voltage effectively, and don't suffer from the same from the back EMF constraints. But while you drive the car in the city, because you have more turns, you are much more efficient. Uh, the trade-off is that you use 2 inverters per machine, which effectively doubles the cost. But as we can see, we can investigate a lot of configurations by exploring the design and market space to see that nowadays maybe the cost is not double. For example, if you parallelize some silicon carbide MOSFETs, if you find some, let's say, hidden vein of gold in the market, you may be able to have 2 smaller inverters than a bigger one and still have a comparable price. Uh, okay, so enough with all this talking. I'm going to discuss how you can create an efficiency map in PSIM. Until now, there were, or let's put it that way, there are 4 different automation, PSIM automation options. The first 3 include scripting. The first one is the legacy PSIM C scripting. There is the Python connection right now, and there is also the Altair Compose with OML syntax. OML is very close to MATLAB. Um, and you can automate PSIM simulations to hit different operating points and get the efficiency maps. Today we'll present a new approach which involves HyperStudy and enables you to do that without any scripting. The only thing you need to do as a first step is to take the envelope of the machine and uh, calculate the this line right here, or approximate this line, in order to be able to put a limit of the points that will be hit inside the automation process. So the way to do that would be to capture these points, the knee point and the final point. You can come up very easily with these equations with the exact formula, and this is the only thing you need to do prior to using HyperStudy. So what HyperStudy does is it takes a PSIM simulation where you can have all the system variables parameterized. For example, you can have of course, there is the torque and speed point. This will be parameterized, but you can also have an inverter that will be using different semiconductors. You can use different switching frequencies. You can use different machine models. You can use different modulation techniques. All these can be variables. And then you need to know the envelope. You need to describe the equation I just showed in the previous slide inside HyperStudy. And then HyperStudy automatically samples this envelope. And it has PSIM solve to steady state for each individual operating point, and it captures the waveforms to steady state, like the torque and speed, the Q-axis and D-axis current. And inside PSIM, you can also do efficiency calculations as well. So there are some tips that I wanted to share with you when it comes to efficiency map creation inside PSIM. I will leave this slide for a few seconds here. but I will take a screenshot of this and come up with these points on the go while I'm actually showcasing an example. Some of the basics, and of course, these will be shared with you after the session. They will be uploaded in Altair community. One of the basic things is that you should use a torque control system, basically use a speed load instead of a torque load to avoid inertia effect and reduce the total time to steady state. If you have ID and IQ references from an FEA tool or from experimental processes, like if you have lookup tables that connect ID, IQ with torque and speed, I advise that you should work with them directly instead of relying in the torque control blocks inside PSIM to come up with the ID and IQ references. Um, what else there is to say here? So when it comes to the time step, using 50 points per cycle is usually okay because PSIM optimizes calculations around switching events and it can give very fast and accurate results. And you can also use steady state blocks and use adaptive, let's say, time steps that are changing based on the switching frequency selection from inside HyperStudy. And please don't use that time. There is no reason for you to use the time where you want to calculate efficiency and different efficiency points. It has minimal effect anyways. Now, when it comes specifically to Flux, I want you to be cognizant that the new PSIM version that is coming this month, version 2025.1, will bring a lot of updates and fixes some issues we have when the lookup table from Flux include non-zero initial rotor angle. So if you watch this webinar in a later time, please work with PSIM 2025.1 or later, and to ensure that you will have a smooth experience. Okay, so now let's get into action. I will open PSIM and I will start with a linear example. So this is PSIM. I'm using a linear model. This is not a Flux IPM model. This simulation is part of our design suites. You can actually already find it if you navigate to Motor Control Design Suite, navigate to the PSIM IPM Drive Torque Control. This is the one. I can actually run it once to see the speed benefit. So this simulation runs in 1 second for steady state. This part of our design sheet. Here is the results. But what I did is I took this example and basically added a few features to help you calculate the efficiency. For example, here, instead of an ideal inverter, I'm using a thermal model. There are a lot of tutorials and material online when it comes to the thermal model. If you're not familiar with it, PSIM has a way to come up with the losses of the inverter really quickly uh, and the only thing you have to do is take the dataset of the device, take some screenshot of the graphs that correlate to conduction and switching losses, and then you can create like devices, thermal model inside PSIM, and then you can iterate between those devices, and PSIM will let you know the losses of these devices. I also added the steady state blocks, so I have the option to stop the simulation when the ID and IQ hit steady state along with the inverter losses. So when the inverter losses stabilize, this is where I'm stopping the simulation. Essentially, this block bypasses this total time option here. It ensures that you are not spending simulation time on calculating things if you are already in steady state. For the efficiency, I'm taking the inverter losses from here. And when it comes to the linear model, we can only calculate the copper losses because there is no 1D tool that has information when it comes to the core losses because that involves geometry and material. You can get the core losses inside PSIM if you include the Flux models. So if you have your motor designed in Flux, you can export it, use it inside PSIM, and this will include the core losses. And this is, in my opinion, very major because we are enabling these insights from the FEA tool inside the 1D simulation. We'll see an example later. Here I'm calculating the efficiency. So I have the copper losses, I have the inverter losses, and I'm making the basic calculations to calculate the efficiency. When it comes to the control, I have a basic field rate control. Here I'm using the torque control reference because I didn't have the d-axis and q-axis reference. Let me run this. So I will be capturing the torque here. As you can see, things look very linear. This is the current, the q-axis current, and this is the inverter losses. So once all this stabilize, PSIM should stop. And now there is a very easy way to automate this for different operating points. Give me a second, my computer froze. Okay, we should be okay now. So I'm going to open HyperStudy, and I'm going to show you how you can automate this simulation to hit all the operating points and calculate the efficiency. So you click on New Study. I'm going to navigate to the specific folder. Okay, perfect. And the only thing you need to do is click Add Model, navigate to the PSIM icon here, navigate to the PSIM simulation. I'm going to select the linear one in this case, and you click Import Variables. When you click Import Variables, the PSIM HyperStudy connector is loading. The first time you do this, it may take several seconds. But once this is done, it brings all of the parameters which are parameterized in PSIM in the parameter files. In this case, I'm also using different devices. I'm using different case temperatures. I mean, I have parameterized them, so I can use different options. I can also parameterize the number of parallel devices in the inverter. There is an option in the thermal model here. And I can also parameterize the gate resistance. So all of these parameters appear inside HyperStudy. Right now, I'm going to deselect everything and just select the commanded torque and the speed load. You click on this button, and this is how you import the variables. So I want you to notice that I'm using a speed load here, and I'm applying torque control. This is important. You don't want to have a torque load here and do speed control. This will be much faster. So let me continue with the analysis. I'm going to put the lower bounds and upper bounds of the torque. For this envelope, I'm going to consider 20 until 200 Newton meters. And for the load, I'm going to start from 1000 RPM up to 6000 RPM. Now, this creates a design space that it's basically a square. In fact, the actual envelope of the machine is not a square because there are the points. These points of the triangle cannot be hit. So we need to put a constraint inside HyperStudy. You can navigate to the constraints, and basically you can put like a torque limit, and you can have your commanded torque be less, let's say when the load is less than 3000, because this is the knee point right here. So the knee point is 3000, the maximum torque is 200. So when the speed load is less than 3000, the torque limit will be 200. And you can type plus, and essentially when the when the speed load is greater or equal than 3000, the actual torque that can be hit is this equation right here. So it's minus 1 divided by 30 times the load plus 300. As you can see, the pass rate is 83.6%, and this is how you define the envelope. Then you click Next, and you click Run Definition. The run definition basically writes and executes the nominal values once, so you can set your the outputs you will be reading from HyperStudy. By the way, this webinar is not meant to explain the complete process of automating PSIM HyperStudy to you. We have plenty of material online, and there's also a step-by-step tutorial on how to do this. This is just to show that you can create an efficiency map without writing any scripting. So I haven't written any lines of code until now. This does not mean that you cannot write scripts inside HyperStudy. If you want to calculate your own outputs and apply your own scripts, like calculating total harmonic distortion or torque ripple, or include a cost function or something, you can use both Python and MATLAB-based syntax in order to do that inside HyperStudy. But the process of handling inputs, outputs, discretizing the design space, and all of this meaningless labor is covered by HyperStudy in a repeatable and shareable way. So you can share it with your colleagues. They can open it 1 year from now, and they can replicate exactly what you did without having to read your code and go line by line. So the model ran once, and we can now bring the results we're interested in getting. So you can click on File Assistant. I'm going to navigate to the results, which will be the .abf file. And then I'm going to take out of the results the torque to make sure the torque is hit correctly. And I'm also going to take the inverter losses and also the efficiency of the system. Going to click Next. Here, I'm going to slice the data to have 3 different data sources and click Finish. So the data sources are saved here. Data sources inside HyperStudy are time series data. Essentially, they are the time domain results out of PSIM. So for example, this is the torque. We can see that it's looking nice and stable. And then out of these data sources, you can get the output responses. So for example, here in the output response section, you can select that the efficiency of the system will be the final value of the efficiency data source. So you can go to the data source, click here, last element, insert, click evaluate, and this is the efficiency for this particular point. Now, the next thing you need to do, the setup is like a template. You do it once, and it just runs one example, which is the nominal values. So 1000 RPM with 100 Newton meters. In order to explore the design space and to build the efficiency map, you need to click Next, Add, DOE, which stands for Design of Experiments. Click OK, and then you just click Next because DOE inherits the options from the setup, so you don't need to reconfigure them again. You don't even have to run it again. You go directly to specifications by just clicking Next. And here you have pre-built algorithms. You don't have to write code that uniformly distribute the points of your input design space. Remember that you have set some lower and upper bounds and some constraints. So HyperStudy, if I go here and type 200, I'm going to select Sobol in this case. By the way, you can click F1 and have a read on how all these algorithms work. But when I click 200 here and click Apply, what HyperStudy does is it takes the design space and uniformly distributes points. So I think you can really tell from these points the actual envelope of the machine. But HyperStudy just created 200 points that are uniformly distributed inside this envelope. Then the only thing you need to do is click Next. Or sorry, not Next. In the evaluation tasks, you can also select multi-execution to have multiple jobs to run in parallel. and you click Evaluate Tasks. And then HyperStudy just starts solving PSIM simulations in parallel. I'm going to stop this. I'm not going to wait for this to finish because I'm cognizant of time. But let me say that for linear models, you can expect results to be really fast in the, let's say, 15 to 20 minutes for 200 points, usually. Uh, but with flux motor models, things can be a bit slower, but you also will be getting a lot more fidelity. And this is where we get to the point of maximizing fidelity to speed ratio. Now, what I mean by that? So PSIM has uh, a nice way to offer you the option to add more fidelity if you wish with lookup table-based approaches, which means you don't really compromise the simulation time that much. Yes, if you add non-linear and non-ideal models, simulations will be slower, but you will be getting much more simulation insights. For example, for the inverter, we can add a thermal device, and this will give us the losses for all 6 switches, for both for the active and the reverse diode path. For the battery, we can add, again, a lookup table-based model of a battery. And for the motor, we can add a lookup table-based model coming from Flux, which means that if you have your machine already designed in Flux, or if you have colleagues that are doing the motor design and are working in Flux, they can export the machine model for you. And this machine model contains information that enables PSIM to calculate spatial harmonics, cognitive torque effects, and saturation effects, and they also come up with the copper and core losses. The core losses part is very important because this is the only way you can get the system level efficiency just in the 1D domain. So without any further ado, I'm going to open the example I have for the flux motor. So instead of 6 or 5 seconds here, when I run this example, it can take much longer, but the torque I'm generating right here is full of harmonics, both spatial harmonics and PWM related harmonics. I can open the results, plot the torque, so you can see that along with a reference, and I can also apply an FFT from inside PSIM. I'm going to make the axis decibels, and here you can see both the switching attribute harmonics. The switching frequency here is 20 kilohertz, but also the lower frequency harmonics, which are attributed to spatial harmonics. The way this works is that both this model and also the control takes into account how the d-axis and q-axis inductances change with different d-axis and q-axis currents and rotor position. The currents have to do with saturation effects, and the rotor position has to do with spatial harmonics. So these are the mechanisms that enable you to calculate this stuff, and the losses you are getting, for example, the core losses, are being, let's say, taking into account the harmonic range currents that pass through the machine. So not only the torque contains harmonics, also when I plot the three-phase current, or rather the AC current, you can see that this is not an ideal AC waveform. This also includes harmonics. But again, the most important thing when it comes to the efficiency maps is that you get the core losses here, so you can add the core to copper losses to get the motor losses, and then you can calculate the efficiency, the system level efficiency, much easier. Now, I want you to keep in mind that adding these models can lead to some controllability issues because of the torque ripple that they have. So, for example, please look at this torque and compare it to this torque. So this torque is just a linear output. And look at this one now. So you may find yourself having some difficulties with different working points. Another reason for that is that LD and LQ change with different operating points, which is like for example, if we're talking about power supply terms, is trying to control a buck converter, and for different operating points, the filter inductance of this buck converter changes. So when it comes to the motor drives, for different operating points due to saturation, for example, the power stage transfer function will be changing. So the phase margin will not be the same with one set of PI controller gains. So I want you to be cognizant of that, but if you use the Flux models, you may have to put some more effort and more expertise into the control design. I also have a slide that covers common issues with Flux models. First one, I just covered it. The control design may require more effort. Sometimes there is also a significant discrepancy between the torque curves generated by PSIM versus the FEA, in this case, Flux motor. In this simulation, there is this speed curve feature. This will be removed from PSIM 2025.1 because this feature, I can also click it, doesn't give very good results if the motor is non-linear, because what this does, it takes the torque equation, this is the equation, and it uses the first LD and LQ that is inside the Flux lookup tables. Remember, I will say it again, these inductances will change due to saturation, while with different currents, for example. So this feature in PSIM didn't take that into account, and we had a lot of users that were asking why. We will remove it, but in case you see this video in the future and you work with versions prior to 2025.1, please be cognizant that this is the reason why. And finally, when you export the LUTs from Flux motor, for example, there is the option for you to disable the rotor position effects. So ignoring the rotor position will still keep the saturation effects in play, but will disregard the spatial harmonics, for example, which will make the torque much smoother and may help you hit some operating points better. Of course, I always advise that you use the reference of D-axis and Q-axis current that comes from your FEA tool, if you have those, because then you will only rely on tuning, you will only have to tune the current control. So inside here, there are two PI controllers. In PSIM, PSIM offers you a way to just define the crossover frequency for the current loop and the torque loop. Basically, it reduces all the control design you have to do in one thing, but this is like just to help you. This is not bypassing the complex control issues that people are facing when it comes to motor drives. Basically, what this does, it tries to have a good enough phase margin based on the setup on your system and the crossover frequency you put here. But this may not always work. You always have to go inside the parameter file and actually check the phase margin. So in this case, it's 83 degrees. It's pretty high. It's very good. But you may notice that whenever you change this crossover I term, the KD and KQ, basically the PI gain parameters will change along with the phase margin, and you should always check that along with the modulation. The modulation is another important thing. Please remember that if you don't get expected results, the first thing you should do, and it's the first thing I do when I receive customer cases, is I look at the modulation signal. We want this modulation to be within the limits of the carrier. And this is set by the V3 parameter here. So this is 1, which means the modulation should always be within plus minus 1. Otherwise, the system will be basically uncontrollable. Here I can see that it's within the range. I can see the nice space vector modulation signal I'm expecting, and I'm pretty sure the results I'm getting are good. So these are the tips for when you use the Flux models. And if you face difficulties hitting some points, please don't hesitate to contact the support. And we will try to help you as much as possible, because this may also involve some things when it comes to how you export the lookup tables. These tips are also covered in this slide, specifically for where you use Flux models. you have to be sure that you use them. For example, in Flux motor, the same maximum current limits and DC bus voltage, and that you export the .mat file for one full electrical cycle. So there are also some options while you export these files that you need to be cognizant of. And then the process of creating the efficiency map would be exactly the same inside HyperStudy. You would basically go here. Instead of loading the linear simulation, you will load the one including the flux motor, and you will redo the same process. And at the end, what you will be getting is something like this when it comes to the efficiency map. If you want a 2D representation, but we can also remember change semiconductor switching frequencies. So we can also see the design space in 3D, or rather in multiple dimensions. Uh, this is a more appropriate example, I think. Let me brought it here. So what I did here is I took all of the experiments of the design space exploration with the DOE. So I basically ran a lot of operating points, not only for torque and speed, but I also changed the semiconductor from the two options you can see in this drop-down menu, and also changed the gate resistance multiplier to change the gate resistance, and also used a lot of different case temperatures for the cooling. And this is the design space. So the blue dots are the design space. And I can then create a fit model for this DOE. Again, there is plenty of material online of how to use fit models. I'm not going to cover this part right now. But essentially what the fit model in HyperStudy does, it applies either a regression or neural networks. So you can also use AI to basically create a reduced order model out of all the design space points. Basically, it's like an interpolation in steroids. HyperStudy is able to go in between the points and assume, based on regression or neural networks, what the actual efficiency will be. And with a click of a button, you have a drop-down menu. You can change, for example, the gate resistance, and you can see the effects. I can change the semiconductor. Oh, I see a big effect here. So this is very nice to visualize the design space and the different options you have for the market as well. And the cool thing, which couples with these multi-level efficiency maps, is the fact that you can apply this in the 1D space to have WLTP cycle simulations that run extremely fast. This brings us to the final points. So this includes the KIV9 example. The scenario one would be how the system would look like with just one inverter per machine. And the second scenario is how the system looks like with two inverters per machine. And here we're comparing both the losses of the system, and we also include the price as well for the semiconductors used. And imagine that you can deploy directly these multidimensional models in our system level tool called Activate in order to get the range of the vehicle for a WLTP scenario. I'm going to skip some slides here. Oh, I'm sorry. My computer doesn't want to cooperate today. But I'm going to open again the simulation I prepared for you. This is inside Activate. So you can go to the report section and export these fit models either as Python fit, called PyFit, which is unique to the Altair ecosystem, or you can also export them as an FMU, which can be used with all tools that support FMU, such as Simulink, for example. So this is the simulation inside our tool to inactivate. The reason I'm doing all this, and I'm not doing this inside PSIM, is because the WLTP drive cycle includes several minutes of actual solve time. So it's like it's a drive cycle. So if you want to have a total time that it's minutes or even hours inside PSIM, this will take forever because PSIM solves the switching effects. PSIM can have an average model inside, but this approach using this lookup, these reduced order models will also give you the efficiency information for every working point, which will come up, with which you can then calculate the energy that is being expended during the WLTP cycle. So this is running right now. This is running, uh, the actual simulation time is 1,800 seconds, and this is completed within 1 minute of simulation or less. So we are running faster than real time, and we are leveraging this. I don't want to call them tricks, but we want to be smart here. We don't want to have, for example, switching simulations when you have a drive cycle. Instead, we used PSIM to generate all of these working points. So all of these blue dots are working points that PSIM reached in, let's say, a total of 20 or 30 minutes of simulation running in parallel to steady state. And then we used HyperStudy to take the design space, which again includes different semiconductors, different gate resistance options, and then encapsulate the design space into a black box, which is a fit model. And then inside Activate, I have those fit models. This is the fit model for the one inverter. This is per machine. This is the fit model for the two inverters per machine. So I can automate this and I can go and select, for example, the drive choice, 1 or 2. If the drive choice is 1, I'm seeing the range I have for the WLTP if I use the one inverter with the one machine. And when I make the option 2, I can see it. I can see the other way around. And this is how you can understand really why big companies like Kia are making these very interesting system level choices, which in the first view doesn't make sense. Why do you want to have like two inverters? But if you see that the actual range you can hit with this choice, it's much better, and you can separate city drive versus highway drive, and the cost is not such a big deal anymore because semiconductors are getting cheaper, for example. This is something very interesting to investigate. Um, Of course, you have to also here model the road load. I'm using some very basic calculations here to calculate the inertia term, the rolling resistance, and aerodynamic drag based on the WLTP cycle. And then I'm having a parameter which is the switch choice. I could have a list, an Excel file with several IGBTs or MOSFETs. I can also set the gate resistance, the case temperature, and then based on every RPM and torque point while the system is running, uh, I can get the efficiency from the reduced order models. I make some calculations here to calculate the total energy that the car is expending, and I'm calculating the total energy for the complete drive cycle and the losses, which really can help me understand the system level trade-offs I need to do. So the process, if I want to summarize, is you start inside PSIM. You decide what is the fidelity you want. You have several options. You can have a drive that runs in 1 second. Here it is. This is the drive. But everything here is ideal. You can have an FEA based, or rather an FEA exporting model coming from Flux. By the way, if you are not using Flux, we also offer a model that enables you to change the LD and LQ values dynamically. This will capture saturation effects, but the Flux model also capture other effects such as spatial harmonics. Then for the inverter, you can also use a thermal device. And all of this will kind of take off the simulation time from 1 second to 5 seconds or 10 seconds, but you will be getting information that are really valuable. And I don't think a lot of tools out there can give you this information in the 1D space. So you start with the basis, the template, which is the PSIM simulation. Then you automate the simulation with HyperStudy. The basic thing you need to remember is that you have to parameterize everything inside this parameter file. Then HyperStudy accesses this parameter file and all of its parameters, and you can define lower, upper bounds. If you want to do tolerance analysis, you can also define some distributions like normal, all of these options. You define the constraints, and then you let HyperStudy uniformly distribute the points with pre-built algorithms. And here you are. HyperStudy has run all of the simulations to steady state. Please take the slides and watch the tips I give and the common problems again and again, because these two slides I created come from actual client problems and may be helpful to you after this session. But you reach a steady state for all operating points, you get the efficiency, and then you can either have a 2D representation of this, or if you change other factors of the system, you will have a multidimensional efficiency map, which can then be deployed inside Activate as a PyFit or inside Simulink as an FMU in order for you to run complete drive cycles. HyperStudy is very convenient. You can add Excel files. You can parse Excel files. You can write your own functions like cost functions. You can probably add a Python API to include components from your ACP system or something. So HyperStudy is very versatile. A lot of people think that it completely takes away things from your power, like you cannot script anymore, but this is not true. The only thing that HyperStudy does, it makes sure that it creates folders for all the examples, run 1, run 8, 7, 6, 5. So for example, if you see, let me get another example. So if you see in the post-processing that a torque point is not good, for example, index 180, you can go directly to the run 180, right here, for example, open it and see what is wrong. All of this creates a seamless experience in debugging a system that needs to hit a lot of operating points, and it's also very easily shareable with your colleagues. And the post-processing results are also very nice to share with your upper management, where, for example, they can have drop-down menus and use multipliers to investigate visually how the system efficiency changes, for example, based on system choices, which is not always easy to do with scripting. Yes, you can do that with scripting, but you have to write code and all of this. And the approach here, as you saw, I just created this in a few minutes. And if you get familiar with that, you can do it as well. So that only leaves a few minutes for questions. I've been waiting for your questions, but I haven't seen any yet. Are there any questions? I see that some people are raising their hands, but can you please type the actual question? Mr. Yuan Gao, I see that you raised your hand. What is the difference between eMachine and Altair? What do you mean by that? What are the advantages over MotorCAD? So I believe MotorCAD is a tool from ANSYS. It's an FEA tool. PSIM is not a competitive tool to FEA, like MotorCAD or uh, Flux or JMag or something. Our competitive solution compared to that would be Altair Flux. PSIM covers the system part, let's say, the 1D part. It provides the harmonic rich currents that include the PWM harmonics inside. You can solve it, and it solve the system basically, like the power stage and the control together. You can investigate control topics as well, and basically it's PSIM covers how you drive the machine much more realistically that you could ever do inside an FEA tool. In an FEA tool, you can define like how the current waveform looks like, if it's an ideal sinusoid, if it contains some harmonics, but the FEA doesn't solve the system, and it's also very slow. So if you work with tools that are not Flux, uh, you can also export lookup tables from there and work with lookup tables inside PSIM. So you can have a lookup table that will change the LD and LQ based on current, for example. If you're interested in that, please, you can contact us through support and we can have a meeting and discuss it. I do not see any other questions, so I will proceed with closing the session. Hope this was interesting. I believe this workflow is providing a no scripting way to come up with efficiency maps, and hopefully it will be a very nice way for all of you to explore system trade-offs much better and create efficiency maps much more efficiently and in a way that it's easily shareable and reproducible.